Well, hello everyone, and welcome to lecture 8 after the Christmas break. And we move on today in our discussions about materials science and engineering. So, today I want to start talking about phase diagrams. I would like you to develop an understanding of phase diagrams to be able to apply this understanding to the change in the microstructure of a metal, and specifically binary metal alloy. So what we mean by a binary metal alloy is an alloy that contains two metals. To relate the phase diagram to how the microstructure of a metal changes as it is cooled from the liquid state, and to be able to look at the phase diagram and calculate the composition of a metal alloy from knowledge of whereabouts you sit on the phase diagram, and hopefully this will make sense as we progress. The first question is, why are phase diagrams useful? Why do we need to think about phase diagrams? Why do we need to study them? And why do we need to understand what they mean? Well, let's imagine that we combine two elements. It could be copper and nickel. And when we combine, let's imagine we take two chunks of copper and nickel separately, we melt them into the liquid state and we combine them. Well, they will mix and they will eventually come to equilibrium. And the question is, what is the resulting equilibrium state in terms of composition and microstructure of the phases involved? And the handy thing about a phase diagram is that if we know something about the composition and the temperature of the system, then we can work out lots of interesting things. We can work out the number of phases that form, we can work out the composition of each of those phases, and we can work out the relative amounts of each of those phases. So phase diagrams are a useful tool. You can think about them a little bit like road maps. And as long as you know the coordinates, and in this case, for a simple phase diagram, those coordinates are composition and temperature, then you can work out a lot of information about the structure and the composition of the material, in this case an alloy, under study. Now, think about a simple phase diagram, and I think that the most simple phase diagram that everyone is likely to be familiar with is the phase diagram of water. So in this case, we plot pressure versus temperature, and we yield a phase diagram that has three familiar phases. Okay, there is a solid, a liquid, and a gas phase there. And clearly, I can use my roadmap here, the phase diagram, where my coordinates in this case are pressure and temperature. And as long as I know the pressure and the temperature that the system sits at, I can yield a lot of information about the physical and mechanical properties of the material in question, right? So I know that if I'm at a temperature of around about 250 to 300 Kelvin and I'm at atmospheric pressure, that is 1 bar, then I'm likely to find water in the liquid phase. If I cool or heat the system, then I cross one of those black lines. I cross something called a phase boundary, and I move into a different phase. So for example, if I heat water up, I heat liquid water up to a temperature above 400 Kelvin and at 1 bar, then it will evaporate and it will change into the gaseous phase. If I cool the system, in this case down to a temperature of 100 Kelvin, for example, at 1 bar, then my water will cross that other black line between the solid and the liquid phase, and it will solidify. So instantly I can tell something just from a knowledge of the pressure and temperature I can tell something about the physical and mechanical properties of the substance I'm looking at. I think how important that is for determining the physical properties of materials that you're going to build with, for example. Now, the interesting thing about water is that its phase diagram has a triple point, the red dot there, and that's where at that precise temperature and pressure, the solid, liquid, and gas phases are all in equilibrium with each other. Water's a unique phase diagram. Before we move on to looking at the phase diagrams, let's think about some definitions that are going to help us to understand what these phase diagrams mean. The first is to cover the idea of a component. These are the pure materials or compounds of which the alloy is composed. So a classic example here is the brass alloy. It's composed of copper and zinc, and the components of brass are themselves copper and zinc. They are separate components which are brought together in the liquid state and allowed to solidify to yield brass. The solvent is the element or the compound that is found in the greatest amount. And conversely, the solute denotes the element or compound that's present in the minor concentration. Now, the analogy here is to go back to high school chemistry and think what happened when you took a spatula full of copper sulfate and you dissolved it in water. Well, here copper sulfate was the solute. It was present in the minor concentration, and water was the solvent. It was present in the greater concentration. That analogy sits well with binary alloys as well, where you're very likely to have one element or compound present in a smaller amount. Now, we can also define something that we call a solubility limit. And this, again, it's helpful to think about this, first of all, from kind of simple conical flask chemistry before we move on to the phase diagrams. The solubility limit is the maximum concentration of a solute that may dissolve in a solvent to form a solution. And if you were to add more solute to a solvent above its solubility limit, then you will get the generation of a new phase, and that new phase will have a distinctly different composition. So let's expand upon that idea slightly. Here I have a phase diagram that is a plot of temperature against weight percent composition. And what it is it's for a sugar compound dissolved in water. So we can, caster sugar, table sugar, whatever, dissolved in water. And the bottom axis, let's focus on the weight percentage of sugar here, that goes from 0 to 100 weight percent. And there is also temperature on the left-hand axis. Let's stay at a fixed temperature for now. Let's remain at about room temperature, 25 degrees Celsius. And let's imagine we're doing this in the kitchen. I take teaspoons of sugar and I begin adding them to a glass of water. Now at room temperature, as I add sugar to water, all I gain is a liquid solution, right? A syrup. The sugar is dissolved completely in water. Okay, think about when you make a cup of tea. Think about when you dissolve sugar in water. It dissolves to form a homogeneous single phase in which the sugar is completely dissolved. Now, at some point, and this will be defined by the solubility limit for that substance in the solvent, so the solubility limit for sugar in water, at some point, as I continue adding sugar to my system, I'm not going to be able to dissolve any more sugar. And we cross a phase boundary, right? We cross the solubility limit. Now we get the generation of two phases above that line. It's above about 65 weight% at room temperature for sugar. No matter how much I stir, if I cross that line, I can't dissolve any more sugar in water. Okay, I can't get any more in there. And I've now got two phases. I've got my original liquid sugar syrup solution, but I've also got a solid sugar solution. Now, the interesting thing about that is that a change in temperature can change the solubility limit. It can change how much sugar I can get in water. So at 20 degrees Celsius, the solubility limit is around about 65 weight% sugar in water. But if I were to heat that up to 100 degrees Celsius, then I can now get much more sugar into the water. I can now get about 80% sugar in water. So just to hammer home what we mean by a phase is a homogeneous portion of a system that has uniform physical and chemical characteristics. So have a look on the left of that phase diagram, to the left of the red line, which is our solubility limit. So the phase on the left of the phase diagram is a single liquid phase, right? It's sugar syrup dissolved in water, completely dissolved. It's a homogeneous phase, it's all one phase, and it has very unique chemical and physical properties. If we cross that solubility limit, if we go over the red line in any way by either increasing, for example, the composition of sugar by weight%, or decreasing the temperature, then we generate two phases. A liquid phase, which is a liquid solution of sugar and water, and a solid phase, which has an additional, which is solid. So this is a heterogeneous system. There are two phases now. And importantly, those two phases have very different chemical and physical properties. One's a liquid, one is a solid. Now, with metals, and we'll focus on metals, and you'll study sort of ceramic and polymeric materials in your final year. But where metals are concerned, and largely we're concerned with binary metal alloys here, so metal alloys that are composed of two metals. You combine two materials, two liquids, and they solidify and they reach equilibrium. And just like the sugar and water system, more often than not, they generate a multi-phase system. Now, the whole point of combining two metals to form an alloy is often to take the best qualities of the two metals in question to make a material that is superior to either of the individual metals on their own. And what happens is that the phases interact to yield a very distinct microstructure. So have a look at the copper aluminium alloy that I show you there. There's a lighter region and a darker region. The lighter region is one phase and the darker region is another phase. And each one of those phases will have a different concentration of copper and aluminium. And that's that the whole process is about the system coming to equilibrium and a balance being found between those phases. Now those phases, the composition of those phases and the structure of those phases, and you can view these down a microscope, as you see the image there, they depend on several things. They depend on the elements that are present, the concentration of each element, the number of phases that are present, how much of each phase is present, and the distribution and arrangement of those phases. And we'll see when we come to study steel that that's also heavily dependent on how the substance has been heat treated. If you like, the thermal memory of the material can be seen in the final microstructure. Now, we tend to describe that equilibrium that's reached in terms of free energy, and this is a thermodynamic quantity. And the free energy is a function of the internal energy of the system and how disordered those atoms and molecules are throughout the system. We call that entropy. A system then will be at equilibrium if that free energy is at a minimum under some kind of specified combination of temperature, pressure, and composition. Now, if you're unfamiliar with the term free energy, don't panic. We are going to look a little bit at thermodynamics of solidification, but it doesn't matter if you're unfamiliar with the term free energy. All you need to be aware of is that equilibrium is reached if the free energy of a system is at a minimum. That's sufficient to know. Now, let's go back to our sugar-water system. If the temperature or the pressure or the composition is changed, then that equilibrium is upset and it has to rebalance, it has to readdress itself again. So let's consider once more our water-sugar system. Let's imagine we have it in a completely closed vessel and we have water in contact with sugar at 20 degrees Celsius. Equilibrium will be established very quickly in that system, and there will be a concentration of 65 weight% sugar and water, because that's the maximum we can get in. If we were to raise the temperature of the system further to 100 degrees Celsius, then I can now get about 80% sugar and water. So I've upset the equilibrium, but the system has responded by changing the amount of sugar that is able to dissolve in water. That's the new free energy minimum for that system at a higher temperature. Similarly, I can change the number of phases by changing either the temperature or the composition. So have a look again at our graph for our sugar-water system. If we take water at 80 degrees Celsius and a composition of 75 weight% sugar, I've got one homogeneous liquid phase. If I were to decrease the temperature, then I cross that solubility line. I cross the solubility limit line. And I've now got two phases present because I can't get as much sugar into my water system as I could at 80 degrees Celsius. So I've now got a solid and a liquid phase present. So by decreasing the temperature here, I've changed the number of phases. Now, of course, that's me talking about a liquid, but if we're talking about metals, and we're talking about a lot of solid state materials, then clearly these phase equilibria involve solid phases. We're not talking about the movement of liquids generally. And diffusion, therefore, is quite slow in solids. We've studied that. So these free energy considerations are useful, but because we've got solid solutions, because we're dealing with solid materials, that equilibrium might not actually ever be reached, or at least the rate of approach to equilibrium is very, very slow. So what might happen is that we don't actually ever attain equilibria, and we end up in some kind of metastable state. Okay, let's have a think about the different types of phase diagrams that we can get for the various types of systems that we're going to come across this year. And this hopefully will also stand you in good stead for your further studies in material science and engineering. So we'll start with a unary phase diagram. Okay, so this is a phase diagram for a single substance. And clearly the composition of this substance doesn't change, right? It's just water in this case. So the composition is held entirely constant, and we plot pressure against temperature. So at any point on these curves, two phases on either side of that curve are in equilibrium. So if I'm on the black line between the liquid and the gas phase, if I'm at the right temperature and pressure, then two of those phases are in equilibrium with each other. The minute I cross one, I jump off the fence, so to speak, and I move entirely into the liquid regime, then we have a single liquid phase. And as I said, there's an interesting point on the water phase diagram in that there's a triple point and all three phases occur simultaneously in equilibrium with each other. Now, the next phase diagram we've got to consider is the binary phase diagram. So this is where we have two components, okay, a mixture of two components. And here we hold the pressure constant, and my y and x axis are temperature and composition. So composition of one of the components, right? Because clearly we've got a two component system, A and B. If I change the composition of A, I can calculate very easily the composition of B. And again, these are little roadmaps that show relationships between temperature and composition and the quantities of phases at equilibrium. And if we know where we are on the phase diagram, we know something about the microstructure of an alloy. So a classic example of a binary phase diagram is the copper-nickel system. So the phase diagram for a copper-nickel alloy. It's a plot of temperature against weight percent nickel, or you could plot it against weight percent copper. And there are some lines that we should be aware of. There is a green liquidus line there, and above that liquid line, the system sits in the liquid state. It is a homogeneous liquid solution that is composed of copper and nickel atoms. If I were to lower the temperature significantly, then my liquid system would solidify and I would be left with a solid that contained copper and nickel atoms, and in this case they would have a face-centered cubic crystal structure. And we call that the alpha copper solid solution, and we've spoken about crystal structure earlier on in the course. Now there's this interesting region here, and we call this the two-phase region. It's the white region that exists between the liquidus line and the solidus line. And here, the liquid and the alpha solid phase are in equilibrium with each other. They both exist. The point that I've circled in red here, below 1080 degrees Celsius, shows that copper and nickel are mutually soluble with each other in the solid state. And we call this an isomorphous solid solution because of the complete liquid and solid solubility of the two components. Now, the interesting thing about these binary phase diagrams is that if we know the temperature and composition, so if we know the coordinates of my roadmap, then we can yield three pieces of very important information. The first is we can very instantly determine the number of phases that are present. We can just look at the phase diagram and rather simply determine that. We can determine the composition of these phases, and we can determine the percentage fraction of these phases. So the number of phases that are present, that's easy because I know if it's a solid or liquid, or I know if those liquid and solid phases are in equilibrium with each other. Number two is the composition of each of these phases. So for example, in the middle region there, that white region, when I have liquid and solid phase that are in equilibrium with each other, the liquid phase won't have the same composition as the solid phase. There might be more copper in the liquid phase, for example, or there might be more copper in the solid phase, and we'll see how you can calculate that in a moment. I can also work out the percentage fractions of these phases. Imagine if I was coming down at 50 degrees Celsius, sorry, from 1500 degrees Celsius at 50 weight% nickel on that graph on the right there. I'm coming down through the liquid phase until about 1300 degrees Celsius when I hit that liquidus line. And as I slowly cross that region down to the solidus line, the percentage fraction of solid phase starts to increase as the temperature cools, as my liquid phase slowly disappears. So let's have a look at some examples of working these things out. So first of all, let's consider the number of phases that are present. An example here, at 1100 degrees Celsius and 60 weight% nickel, there are my coordinates. I can follow those and I can show where I am on my roadmap, and I'm well into that solid phase. So I know that there is one phase here, and it's composed entirely of the alpha solid phase. If I were to raise the temperature, if I were to consider a temperature of 1250 degrees Celsius and 35 weight% nickel, then I'm right in the middle of that two-phase region whereby the liquid and the solid phase are in equilibrium with each other. So here I know that I've got two phases present. So the number of phases present are two, and they are the alpha solid phase and the liquid phase. Now I can also work out the composition of these phases, and this requires a little bit more detail. For the one phase regions, I know that there is only one phase present. So for example, at a temperature of 1320 degrees Celsius, there is only the liquid phase present, one phase, and when we have a one phase region, the composition of that phase can be read from the x-axis. So it's that the composition of that phase is 35 weight% nickel. Similarly, if I were to lower the temperature of that system down to 1190 degrees Celsius, I now have just one phase, it's the solid alpha phase, and I can measure the composition of that phase from the x-axis yet again, which is 35 weight%. It becomes slightly trickier when you have a two-phase region. So let's go back to 1250 degrees Celsius and 35 weight% nickel. I know that I have two phases present, okay, and I know the overall composition of the alloy is 35 weight%, but I don't know the composition of the liquid phase, and I don't know the composition of the alpha solid phase. So what I've got to do is I've got to imagine that there is a tie line. We sometimes call this an isotherm, and we extend that tie line across the two-phase region at the temperature we're at, and we terminate it at the phase boundary line on the other side. So in this case, we terminate our tie line at the liquidus line and the solidus line. So I construct my tie line and I drop perpendicular lines down to the x-axis, down to the composition axis, and I read the composition of each phase. So where I've dropped my perpendicular tells me the composition of the liquid phase is 32 weight% nickel, and the composition of the solid phase is 43 weight% nickel. So I know that at that temperature and composition, I've got a liquid phase which has 32 weight% nickel and a solid phase which has 43 weight% nickel. Now, the other interesting thing that I can do is I can work out the percentage fractions of these phases. So, for example, at 1250 degrees Celsius and 35 weight% nickel, how much liquid phase is present and how much alpha solid phase is present? Well, again, I construct my tie line. I note the overall composition of the alloy, which is 35 weight% nickel. I drop my perpendiculars, and I take the length of the tie line from the overall alloy composition to the phase boundary for the other phase, or the opposite phase to the one I'm trying to work out, and divide it by the total length of the tie line. I'll show you how to do that now. So in this case, let's imagine that we're calculating this for the 1250 degrees Celsius 35 weight% nickel alloy sample. I construct my tie line at 1250 degrees Celsius. I note the overall composition of the alloy. I drop my perpendiculars, and if I were to calculate the percentage fraction of the liquid phase, then I take the length of the tie line from the overall alloy composition to the phase boundary for the other phase, in this case the solid phase, and I divide by the total length of the tie line. So in this case that's 43 minus 35. That tells me the length of the tie line from the overall alloy composition to the phase boundary for the other phase, and I divide it by the total length of the tie line, which is 43 minus 32. The answer I get is 0.73, and I can do exactly the same for the liquid phase, and the answer I get is 0.27. You can think about these tie lines as acting as a little bit of a lever or a balance. They're a bit like visual representations of the equilibrium. What I want to do now is have a look at what's going on a micro scale. What's going on in the metal as we cool it from the liquid state right the way through to the solid state. Because we want to examine the microstructure as we cool one of these alloys, one of these isomorphous alloys. So let's assume that we cool the sample very slowly. The reason why we consider cooling the sample very slowly is because we're going to assume that equilibrium is maintained here. So we cool it slowly, we give the atoms enough time to diffuse and the system enough time to readjust and reform that equilibrium. Small and slow changes in temperature will yield to readjustments in the compositions of those phases and the relative amounts of those phases. And that's because we're allowing the diffusional processes that need to happen, the rearrangement of matter on the atomic scale, to redress that equilibrium. So let's start with our 35 weight% nickel alloy, and let's start at 1300 degrees Celsius. At 1300 degrees Celsius, the system is in one homogeneous phase, it's in the liquid state. Have a look at the vertical dashed line. That's the line we're going to go down through as we cool the system. I begin to cool the system from 1300 degrees Celsius, and there are absolutely no microstructural changes until I hit that point there, B, the liquidus line. When I hit point B, very small amounts of the alpha solid phase begin to form because we're cooling it down. But there are only small amounts. The percentage fraction of solid phase is still low at this point because we're still at quite a high temperature. But importantly, the moment I cross this liquidus line, there are now two phases present. As I move down that line, the percentage of solid will start to increase. But for now, it's relatively low. But importantly, there are two phases present. As I move down to, let's say, 1250 degrees Celsius, or point C here, then I've still got two phases present. But the composition of those phases looks different. There might be more copper now in the solid phase, for example, and there might be more, the amount of nickel will change in the liquid phase. And that's because the system is responding here and readdressing that equilibrium. As I get to point D, as I reach the solidus line on that diagram, the solidification process is very, very nearly complete. So the percentage fraction of solid phase now is very, very high with a very, very small amount of liquid phase. And of course, upon crossing that solidus line completely, any remaining liquid in the system solidifies, and the solidification process is complete, and I have a fully polycrystalline alpha solid phase material. Now, that described what happens in equilibrium cooling, but in virtually all practical solidification situations, the cooling rate is far too quick for equilibrium to be established, and you get the development of microstructure within the material. And we'll talk about this in much more detail as we progress over the next few lectures. But just to introduce this concept, because diffusion is very slow in the solid phase, new alpha domains form and their composition continuously changes from a radial position. So think about a solid phase starting to nucleate. You get an initial grain of solid, right? And that will have a very defined composition. But as the material begins to solidify further, because diffusion is slow, the next alpha grain that solidifies will have a lower weight percent nickel content. And this continues in this radial manner. What it leads to in binary systems is the generation of things we call core structures, where there is a concentration gradient that's established in that radial manner that I show here. And the center of those core structures is rich in this case, the high melting point element. And the outer is rich in the low melting point element. And the problem with this is that as it experiences reheating, let's say you've got it in a situation where you want to reheat it, the outside starts to melt. And because the outside starts to melt, you get a sudden loss in the mechanical integrity of the structure. So that's something you've got to think carefully about. There are some questions here for you to have a go at. What I will do is we're going to do a couple of revision sessions as part of this module. So what I will do is I will go through these in the revision sessions for this module. But for now, have a go at them.